Welcome back to this course on principles of polymer synthesis, and today is the 7th class, and in this class we are going to continue our discussion of principles of step polymerization. So, let us go back to the derivation that we were making as far as the kinetics of step polymerization is concerned. We were talking about self catalyzed reactions. In this case we are taking polyesterification as an example. So, let us go back to the derivation right where we left it. So, we had actually derived an expression for xn bar, which is the number average degree of polymerization, and this number average degree of polymerization was equal to 1 divided by 1 minus p. Now, this particular expression is valid when you have stoichiometric amount of starting materials. So, this is your Carothers equation. Now, if we go back to the particular expression that we had got, 1 divided by 1 minus p square equals to 2 m 0 square kT plus 1, that is for self catalyzed reactions. And if we use this particular expression here, then what we have is xn bar square equals to 2 m 0 square kT plus 1. So, which means that basically the number average degree of polymerization square of that is varying with T linearly. Now, this number average degree of polymerization, by now you might know from our previous discussion on degree of polymerization, that is the average number of structural units per polymer chain. This has a direct relationship with the molecular weight of the compound. So, before we go further on this, what I would like to do is to take a very simple example and tell you what this actually means here, this xn. So, again we will take this example of ethylene glycol and adipic acid. Let us draw the repeat unit here, OCH2 CH2O, and then you have CO CH2 whole 4 CO2H. So, in fact this will be CO like that. So, what is the molecular weight of this repeat unit? If you just add things up, it becomes 172. Now, in this repeat unit you basically have two structural units. So, the average molecular weight per structural unit for this particular polymer, then it is 172 by 2, and that will be equal to 86. Now, there are different conventions with regards to this. Sometimes what people will tell is that they will take the total of 172 itself, but the other convention which is generally more accepted is that if you have n number of structural units per repeat unit, then you have to take the average molecular weight of the structural unit, which means you have to divide by n. So, in this case you have to divide by 2. So, 86 you call it as m 0, that is the average molecular weight per structural unit. Now, m 0 bar let us say, or m 0 you can put. So, what is the number average molecular weight for this particular polymer? That will be then the average molecular weight per structural unit into the degree of polymerization. So, total number of structural units you are multiplying by the molecular weight per structural unit, average of it, and you then add the molecular weight of the end group, then that becomes your number average molecular weight. Now, this molecular weight of the end group, it can be regarded as 0 for all practical purposes, because if the polymer is of very long chain, then that end group, the contribution to the total molecular weight becomes insignificant. Suppose you have 1000 units together in a polyester and you have an alcohol on one side, that alcohol is how much? It is oxygen 16 and hydrogen is 117 only. So, you can actually neglect, or you may have maybe 20,000 units. So, that part you can neglect. So, for all practical purpose, then Mn is equals to m 0 into xn. So, in this case your Mn equals to m 0 into, so m 0 is 86 into xn. Now, let us say your xn bar is let us say your xn bar is 50. I mean you are actually targeting a particular number average degree of polymerization for your purpose. Let us say you are targeting xn bar equals to 50. Then what is the molecular weight you will get? Your molecular weight will be 86 into 50. So that will be 4300. What about xn bar equals to 100? If you are aiming for a higher molecular weight, let us say you are aiming for degree of polymerization 100, then what is your Mn? Mn becomes 86 into 100, Mn bar becomes 8600. So you are beginning to get polymer of some practical significance. As I told, in general at least 5000 should be the polymer molecular weight. So then the properties start to manifest, say mechanical strength, so on and so forth. So you see, in general if your xn bar for a polymeric system is 100, then your number average molecular weight is round about 10,000, in that range. It may not be 10,000, depends on the structure and all, it is in that range. So what you are targeting for this kind of step polymerizations is your xn bar at least in that range, say 100, then you get 8,000, 9,000 molecular weight. If you want a molecular weight of say 50,000, then you need a correspondingly higher value of xn. Now in order to achieve this value of xn or xn bar, whatever the degree of polymerization, how much the reaction has to proceed? This will be given by your Carothers equation. So you know your Carothers equation is xn bar equals to 1 divided by 1 minus p. So in order to get xn bar 100, if you put that value here, what is the value of p? The conversion or the extent of reaction, that is 0.99. So you need 99% of the reaction. So 99% of conversion is required in order to get an xn bar of 100, which will give you only a molecular weight of 8600 for this particular system. What about xn bar 50? If you put xn bar 50 here, then your p becomes 0.98, and xn bar 50 means your Mn bar is 4300. So you have molecular weight of only 4000 approximately, even if you have gone up to 98% of conversion. So when you go to 99% conversion, then you have molecular weight of 8600. So you have to go beyond 99% conversion in order to get say molecular weight 2000 or something, 20,000 or something. So even 98% of conversion is not sufficient for step polymerization. And you know a 90% conversion in normal organic chemistry labs is regarded as excellent, but that is a disaster then for step polymerizations. How much time is required and all, we will come to that. If you remember in this particular slide here on the in this particular page on the top, if you see here, this is the expression or this is the expression xn bar, how xn bar square is related to time for self catalyzed reaction, that changes linearly with time, but that changes actually slowly because time is related to the second power of degree of polymerization. So with time it will increase, but it will increase rather slowly. So what will happen if you consider a different scenario, that is if you are using an external catalyst. So you know that xn bar is related to time, and we have not yet told you this in order to go from 98% to 99% of reaction, how much time is necessary and all, those we will tell you after discussing these things here. So let us now talk about the external catalysis. We talked about the self catalyzed system, now we are going to talk about the external catalyzed system. Now I am not going to derive everything here. So here I am going to start from this particular expression, your minus d CO2H dt, that is the rate of the reaction, is basically your K3K, recall that particular expression there, into CO2H into OH into HA, and both of CO2H and OH, these concentrations are the same to start with because it is stoichiometric. So this becomes square, and we do not replace HA with CO2H because we have added a mineral acid, small amount of a mineral acid as an external catalyst. So this stays here, but since this is the catalyst, this concentration is constant. So basically this can be incorporated into this constant. So you just remove this and you incorporate that into this constant. Again this is capital K, this is small k. So, let us say small k prime, and then it becomes CO2H whole square. Now, you do the same way. In the same way, what you do is you do an integration, the CO2H you can replace by m. So, minus dm by m square equals to k prime dt integral 0 to t integral m0 to m, and if you do the calculation here, what you will get is 1 divided by 1 minus p equals to m0 into k prime t plus 1. This 1 divided by 1 minus p from Carothers equation is x n bar, that is equals to m0 into k prime into t plus 1. So, you see here your x n bar is linearly changing with time, but if you compare that with this particular graph here for self catalyzed reaction, you can immediately see that the time is varying with the second power of x n bar square for self catalyzed reaction, whereas it is varying directly with x n bar in the external catalyzed reaction, which actually means that this slope of this particular curve is much steeper with respect to this. So, in effect your degree of polymerization will increase much faster with time or with conversion if you compare, if you are using an externally catalyzed reaction. So, for all practical purposes then your self catalyzed reaction you do not use, because the reaction will take so much time in order to get to an xn which is acceptable to you. It is actually inconceivable in industrial situations. Here within a reasonable amount of time you can develop the xn bar. So, if you just plot them together, so this is xn here, and if you are plotting xn bar square, that will be something like this. So, same time it will be developing the degree of polymerization or the molecular weight, the polymerization, it will be going much slowly, the molecular weight will be developing much slowly. So, we will then say that external catalysis is the reasonable conclusion, that is what you are going to do always for this kind of reactions, say especially for polyesterification reactions. Now, one more thing I would like to point out here in regards to a previous discussion, that people thought some reactions were very slow, they thought the size is very big for the polymer. So, the functional groups are reacting slowly. So, the functional group reactivity has become lower, in direct contradiction to the assumption that we had that the functional group reactivity does not change. So, one of the reasons was also this, that when people used self catalyzed reactions, the reaction was very slow. So, they thought when the size is very high for the polymer, maybe the functional group reactivity has dropped. But later on when they realized that this is the kind of analysis that you can do, you can add little bit of mineral acid and the reaction will go very fast, because your xn bar or the degree of polymerization directly varies with T rather than the square of that. So, now if you take this particular expression here, you will see that, I mean, if you do a calculation, if you do the maths here and if you compare with the previous page here, if you are having an xn bar say 50 and xn bar say 100, we told this is for 98% reaction, this is for 99% reaction. If you compute the T correspondingly, the T basically will become for this particular reaction approximately, say the T will be say 450 minutes. As a matter of fact, I mean you can put in this particular equation also, but if you look at the exact experiment that was done in order to derive this, it is not ethylene glycol that they used diethylene glycol in that case. So, the point is the time that it takes in order for the 98% of the reaction to be completed, the time that it takes for 99% of the reaction to be completed, it was 850 minutes. So, from 98 to 99%, for this 1% of the reaction you had to wait double the amount of time that you had to actually wait for the first 98% of the reaction. So, you know how difficult it is, but you have to actually wait for this extra time, because if you stop at 98% you get only 50 degree of polymerization, your molecular weight is only around 4000. If you want more than 8000, 9000, you have to wait for this double amount of time. Now, this kind of problem is there for step polymerization. Towards the end, each percent of conversion will take almost like double the time, say from 98% to 99%. So, I hope that this particular small calculation has given you the idea of the importance of this kind of analysis of kinetics, because if you did not do this kind of analysis, you would not know what are the things that you need to do to achieve high molecular weight. So, these equations then show you need to go at least to 99% of conversion in order to get reasonable molecular weight for your polymer. Okay. So, now let us move on with this particular discussion to something else. Now, we have talked about these reactions as equilibrium reactions. These are equilibrium reactions which needs no further explanation, that you have to remove the water from the system. What happens if you do not remove water? What happens if you do the reaction in a closed system? You do not remove any of the products. After some time, when enough amount of the product has developed, then the backward reaction will be fast enough and the depolymerization will take place. So, an equilibrium will be reached. So, you have to find out if you can at all do this reaction in a closed system, if it is acceptable at all in terms of the yield. So, if you are looking for a closed system here, so let us say you have a closed system here and you consider the same reaction with an external catalysis. So, you have an acid, you have an alcohol. Now, I will draw the full reaction in one go. You have your product here, ester, and you have water. So, this is in equilibrium, it has reached equilibrium, it is a closed system. Now, in this particular situation, let us say you started with a concentration of m0 for both. When the equilibrium has been reached, let us say the conversion, I mean the extent of reaction is PE, E stands for equilibrium situation. So, at equilibrium, what is the concentration of this m0? It will become m0 minus m0 into PE, same concentration will be for this. What will be the concentration of the products? It will be PE into m0 and this will also be PE into m0. So, if you write down the expression of equilibrium constant, which is nothing but small k1 divided by small k2, which is equal to, say, this product we write as the ester, we write as COO, and water is water here concentration, and this is CO2H starting material, and this is OH. So, this will be then PE m0 square on the up, and on the bottom it will be m0 into 1 minus PE square. So, this m0 will go, and if you do the final calculation, what you can find out is small PE, which is your extent of reaction, it will be equal to k to the power half divided by 1 plus k to the power half, and your xn bar, which is nothing but 1 divided by 1 minus PE, Carothers equation, that will be equal to 1 plus k to the power half. So, the point that we want to find out here is, can we have acceptable degree of polymerization at very high conversion? Very high conversion is not at your hand, because conversion is limited by the fact that equilibrium has been reached. So, conversion has stopped, that is your PE. So, in that equilibrium condition, can you have high enough value of xn so that this reaction is acceptable to you? That will depend on the equilibrium constant. If the equilibrium constant is high, then you can get a very high value of xn, because xn will be equal to this, it cannot go higher than this value in equilibrium situation. Now, let us have some data here in order to consolidate this idea. In fact, this data can be derived, you put the value of k, some values of k, correspondingly you can calculate the value of PE and xn, and you can have some kind of realization of what is the situation here. So, k, and then you have PE, and then you have xn bar. So, if your k is 1, only 50% of reaction occurs if the equilibrium constant is 1, and your xn bar is 2, it is like an oligomer. If your k is say 81, then 90% of reaction has occurred, your xn bar is only 10. So, 90% of reaction is not acceptable to you, molecular weight will be very low. If your k is 2401, then 98% of the reaction will occur at equilibrium, xn bar will be only 50. 9801, 99% of reaction, xn bar is 100, it is becoming reasonable. 39,601, 0.995, xn bar is 200. Now, as I told, in general for your typical step polymers, when xn bar is 100, your molecular weight becomes around 10 to the power 4. So, you have to go beyond that. So, you need this kind of situation. So, your equilibrium constant has to be as high as this in order to get this kind of reaction, extent of reaction will be then 99.5% and your Xn bar will be 200, reasonable maybe. So, for a reaction to be successful in a closed situation, your equilibrium constant has to be very high, at least in this range. It cannot be even say you have 3000, 4000, your Xn bar is not good enough. So, let us look at what are the typical K values or equilibrium constant values for your typical step polymerization reactions. Say if you are looking at polyesterification reactions, your typical K values are of the order of 10, they do not normally go beyond 10, I am just putting 1 to 10. So, if the K value is say 10, you are getting Xn value very very low, this reaction cannot work. If you are looking for polyesterification, you cannot do in closed system, you cannot simply get high enough degree of polymerization which will lead to high enough molecular weight of the product. Even for polyamidation, your K value is 10 square to 10 cube in the range of 1000 for polyamidation. So, how much you can get? You see, you need at least around 2400 to get Xn value of 50, which for the reaction of adipic acid and ethylene glycol, it came to around 4000 the molecular weight, still quite low. So, even polyamidation will not work. So, the conclusion is that you cannot do these reactions in closed system, you simply do not have high enough degree of polymerization, simply cannot have high enough molecular weight for industrial application. So, you need an open system, and when you are doing an open system, in principle it will ultimately reach an equilibrium. So, you are removing water. So, how much of water you have to remove in order to get an Xn bar or the degree of polymerization that you want, that becomes a question. That is why this kind of analysis is necessary. You want to have a target of molecular weight, this range I want to get. So, correspondingly what is the Xn bar, degree of polymerization, and correspondingly to what extent the reaction has to progress. So, that will tell you how much of equilibrium concentration of water has to be there in order to shift the equilibrium towards the product, so that you can get that kind of molecular weight. So, if you do the same analysis for an open system, then your expression is something like this, your equilibrium constant, the same equilibrium constant expression, until now I am not modifying anything, it is like this m0 into 1 minus p whole square. Now, here your Pm0 is basically, so you have Pm0 into Pm0 divided by m0 square into 1 minus p square. Now, one of the m0s you can remove. Now, Pm0, it is the concentration of water as well as the concentration of the ester at conversion P. So, you can just replace this Pm0 by water and P into concentration of water, this P stays there, and then you have m0 at the bottom, and 1 divided by 1 minus p whole square is nothing but Xn bar square, Carruthers equation, you already derived that. Now, you know your Xn bar is equal to 1 divided by 1 minus p. So, you can correspondingly you can derive the expression of p in terms of Xn bar. So, which is nothing but Xn bar minus 1 divided by Xn bar. So, you replace p with that, and then what you will get is your k will become equal to Xn bar minus 1 into concentration of water into Xn bar divided by m0. So, ultimately the concentration of water that you will be having at equilibrium is nothing but k into m0 divided by Xn bar into Xn bar minus 1. So, it shows that in order to get a higher value of degree of polymerization, you need to remove water more. So, the lower is the concentration of water at equilibrium, the higher is the value of this degree of polymerization. So, basically this Xn bar you want very high. So, Xn bar minus 1 is close to Xn bar. So, typically your water then concentration of water is proportional to 1 divided by Xn bar square. So, what it tells you also this equilibrium constant, if your equilibrium constant is higher, you can remove actually lower amount of water to obtain the same high value of Xn bar, because this water, this concentration here is the equilibrium concentration. So, if you remove, so this K and water they are actually varying in a similar way. So, if your equilibrium constant is higher, in order to get the same value of Xn bar you have to remove water less, which becomes easier for you. So, actually you would like to have a reaction with high equilibrium constant, so that you have to remove less amount of water to obtain the same degree of polymerization if you are comparing those things. So, that way if you are looking for, say for example, polyamides, I already told you polyamides have a higher equilibrium constant of 2 orders or 3 orders of magnitude than polyesterification. So, polyamide reactions will be easier to do in open condition than polyesterification. Closed condition, forget. Open reactions, polyamidation will be easier reactions for you. Why is that so? Because your K value is very high in comparison to your polyesterification. So, if K value is high, so correspondingly you have to actually take out less amount of water. So, if I show you a table like this, so let us say your concentration of your starting monomers is around 5 molar, and then this is the K value, and you are putting your Xn bar here, and water is moles per liter. So, K value of 0.1, Xn bar, so Xn bar you are always looking for 100, say. So, if K is 0.1, the equilibrium concentration of water that you have to achieve is this. That means you have to remove water until you have this much low concentration. The lower is this value, the more is the difficulty for you. That means you have to actually remove more water. So, if K value is say 81, in order to achieve the same degree of polymerization, your equilibrium concentration of water has to be in this range, much more manageable. If the K value is 361, then it has to be 0.183 moles per liter. So, if you have to remove water in order to target this concentration, final concentration of water, and if you have to remove water in order to target this concentration, you would better do this, because this is easier for you, and that can only happen when the equilibrium constant for that reaction is high enough. That helps you in this respect. All of them you want the same molecular weight, which is designated by Xn bar corresponding to Mn bar. So, that is why the polyamidation is basically easier under this kind of situations. Okay. So, the kinetic analysis for the moment is complete as far as I thought is required for this level of the course. So, what we will next start is molecular weight control of the reactions. And as I am telling you here, when I am talking about molecular weight control, I am really saying that you want a precise range of molecular weight. I mean, you want to be as much precise as possible. Of course, you want to decrease the polydispersity, as I was telling before in the previous week, Mw by Mn, you want to have lower distribution of the molecular weight. So, for that you are looking for special techniques and all, but the aspect here I am going to tell for this kind of reactions, say you want a particular Xn bar, suppose you want 100, then you have to reduce the water to a particular value concentration, final equilibrium concentration corresponding to the equilibrium constant value of that particular reaction. Now, you might say I would like to reduce the concentration of water even further. You can. If you reduce the concentration of water even further, probably you can go to higher molecular weight, but that is not desirable for you. You want a specific molecular weight. You do not even want to go higher than that, because certain properties may become undesirable. As I am telling you, the processability may become difficult for that. So, that is why what we will do next is we will have a discussion on the how you can control the molecular weight for this kind of step polymerization. We have a few minutes left in this particular class. So, we will just give you an introduction to that for the moment, and then we will continue in the next class. So, when you are trying to control the molecular weight, say again you are reacting a diamine with a dicarboxylic acid. So, what will happen if you are using stoichiometric amount of both, the final product will have an amine on one side and carboxylic acid on another side. And typically what you do is that at a particular time you want to stop that particular reaction, because the time is related to your Xn bar degree of polymerization, which is related to your molecular weight. So, when you are stopping, essentially what you are doing is you quench the reaction. Many times you decrease the temperature and then you quench the reaction. That is all well and good, except for the fact that later on the reaction has to come back to room temperature or slightly higher temperature when you are trying to take it out or whatever. Then what can happen is that you have potential reacting groups at the end of polymer chains. Let us say each polymer chain, one end is amine, one end is carboxylic acid. So, that polymer chain has a potential to react with another polymer chain. The amine of that polymer chain can now further react with the carboxylic acid of another polymer chain. This is something that can happen, and that can actually play havoc with your molecular weight. So, that is not a good control. So, one of the ways will be to use a slight excess of one of the starting monomers, so that excess monomer at the end will be shown as the functional group at the end of the polymer chains. So, if you have a diamine and a dicarboxylic acid reacting, and if you take a slight excess of the diamine, at the end of the reaction what we will have is a polymer chain. On both sides of that there are amine, because the acid reactant it was in lower quantity. So, it has been completely used up, still there were amines left. So, that reacted, now both ends are amine, though amine cannot react with itself that way. So, then the polymer chain becomes unreactive. So, we will discuss this and more in the next class. Till then, thank you for your attention.